Welcome to the Deep Dive. Today we're embarking on, well, an incredible journey, really, exploring the most extreme phenomena in the cosmos.
Absolutely. We're talking stars, black holes, the universe itself, from birth to death and maybe beyond.
Exactly. We're diving into everything from, the life cycles of stars, the crazy physics around black holes, all the way to the universe's origins, and even how it might all end.
And our mission here is to sift through some really fascinating material, YouTube deep dives, scientific papers, you name it. We want to pull out the key insights, the surprising facts.
So you can walk away feeling like you've really got a handle on these huge, sometimes mind-bending topics.
That's the plan, make the complex a bit more accessible.
Okay, let's jump right in with stars then. It's kind of amazing that a star's entire life, its whole story, is basically dictated by just one thing, its mass.
It really is the defining factor. Take smaller stars like our sun or anything below about 8 times its mass. Their journey is, well, less explosive than their bigger cousins.
Less explosive, but still pretty dramatic for us, right? I mean, our sun becomes a red giant.
Oh, absolutely. In about 5 billion years, yeah. Once it runs out of hydrogen fuel in its core, the core shrinks, heats up, and starts fusing helium. But hydrogen fusion keeps going in a shell around that core.
And that puffs up the outer layers.
Massively. It'll swell up into a red giant, easily engulfing Mercury, Venus, possibly even Earth. It's a dramatic transformation.
Wow. Okay, so that's the red giant phase. What happens after that for these more common stars? You said 97% of them.
Yeah, a huge majority in the Milky Way. So their cores just don't get hot enough to fuse carbon. You end up with this inert carbon core building up.
Inert, meaning no more fusion.
Exactly. So eventually all fusion stops. The outward pressure that was holding the star up just disappears. It's like a tug of war where one side lets go.
And gravity wins.
Gravity wins. The outer layers collapse inwards, and the core gets squeezed down into an incredibly dense object called a white dwarf. It's only supported by the quantum pressure of its electrons being squeezed together.
Okay, so white dwarf is the end for most stars. But for the really massive ones, say over 10 times of a sun's mass, it's a different story. Much more violent.
Oh, much more. These stars have incredibly hot cores. They can fuse heavier and heavier elements, carbon, oxygen, silicon, building up layers like an onion.
An onion of fusion.
Sort of, yeah, until they reach iron in the core. And iron, well, iron is the sticking point. Fusing iron actually takes energy, it doesn't release it.
Ah, so the energy source at the center just turns off.
Yeah.
Or worse.
Worse, it becomes an energy sink, the pressure support vanishes almost instantly, and the star's own immense gravity just crushes the core.
Does anything stop the collapse this time?
Sometimes. The collapse can be so intense it forces electrons and protons together to form neutrons. If the star isn't too massive, this forms a neutron star unbelievably dense, supported by neutron pressure. But the collapse itself triggers a massive rebound shockwave.
The supernova.
The supernova, a catastrophic explosion blasting the star's outer layers, all those heavier elements it created out into space. It's incredibly bright, incredibly powerful.
But what if the star is even more massive? Too massive even for a neutron star.
Then gravity wins completely. Nothing can stop the collapse. It just keeps crushing down, smaller and smaller, until it forms a black hole, a singularity cloaked by an event horizon.
It's wild, isn't it, that the biggest stars live the shortest lives? You'd think more fuel means longer life.
It's counterintuitive, yeah. But that immense gravity means they burn through their fuel at a furious rate, like millions of years instead of billions for stars like our sun.
And this brings us to cosmic recycling, right?
Yeah.
These supernovae aren't just endings.
Not at all. They're crucial beginnings. They seed the interstellar medium, the gas between stars, with all those heavier elements, carbon, oxygen, iron, gold, everything heavier than helium, basically.
Which then gets swept up into the next generation of stars.
Exactly. So you see this evolution over cosmic time. The first stars, theoretically, were made of almost pure hydrogen and helium from the Big Bang. We call them population third.
Then stars like population 2 formed from gas lightly enriched by those first supernovae.
Right. And then population I stars, like our sun, formed from gas that was even more enriched by previous generations. They start life with a higher fraction of these metals, as astronomers call them.
It's like that mammoth and elephant analogy you mentioned. Different generations, related, but evolving characteristics based on their environment, or in this case, the available materials.
It's a great way to think about it. The universe's stellar populations change over billions of years.
But finding those first ones, population third, that sounds tough. especially if they were massive and died quickly?
It's incredibly challenging. They're the needles in the cosmic haystack. They should, in theory, be made of just hydrogen, helium, maybe a tiny bit of lithium and beryllium from the Big Bang, nothing heavier.
So no metals in their spectra.
That's the hope. Spectroscopy is the key tool, looking for starlight that's completely clean, lacking the absorption lines, the fingerprints of heavier elements.
But you mentioned simulations are helping now.
They are. Hugely. Modern simulations modeling dark matter and gas physics in the early universe are getting sophisticated enough to explore possibilities we couldn't before. Like, maybe not all population 3 stars were huge monsters. Maybe some smaller ones formed too, ones that could have survived until today.
Okay, so simulations give us clues on where and maybe what to look for, but the actual finding.
It's cosmic archaeology, truly. Even if a low-mass population 3 star survived, it spent billions of years floating through the galaxy.
Collecting dust, or well, gas and heavier elements.
Exactly. It's likely covered in billions of years of pollutants, as one source put it. Heavy elements accreted onto its surface over time, creating false spectral lines, making it look like a younger, more metal-rich star.
So you had to somehow see through that contamination.
You have to do incredibly careful, intensive work, like an archaeologist carefully brushing away layers of dirt, and requires very high-resolution spectra and detailed analysis.
Where's the best place to even start looking?
The Milky Way's halo seems most promising. It's this big, diffuse sphere surrounding the main disk of our galaxy.
Why the halo?
Well, it's less crowded, fewer stars to sift through compared to the disk or bulge. And critically, it's known to host some of the oldest stars in our galaxy. So if ancient population 3 survivors exist, the halo is a prime hunting ground.
Makes sense. Okay, so from stars, their lives and deaths, we inevitably get to black holes, the ultimate gravitational victors. Let's redefine that core concept again.
Simply put, yeah, a black hole is a region of spacetime where gravity is so intense that nothing, not even light, can escape once it crosses a certain boundary.
The event horizon.
The event horizon, the point of no return.
The simplest kind is the Schwarzschild black hole.
Right.
No spin, no charge, just mass.
That's the one. Discovered mathematically very soon after Einstein published general relativity. It's perfectly spherical, static, unchanging.
But inside.
Oh.
At the very center, the singularity.
The singularity. A point where the curvature of space-time, according to the theory, becomes infinite. Density becomes infinite. Our physics, GR, basically breaks down there. It tells us we need a deeper theory, probably quantum gravity.
And mathematicians have found ways to map this space-time, revealing more about its structure.
Yes, using different coordinate systems, like different ways of drawing a map. Some of these maps, like the Kruskal-Sekeres coordinates, show the full theoretical structure, which includes not just the black hole region we fall into, but potentially connections to other regions, like a white hole, a theoretical time-reversed black hole where things can only exit, and even hints of regions beyond the singularity.
Wild theoretical possibilities. But focusing on the outside, how do things behave around a Schwarzschild black hole, like orbits?
Okay, so far away, gravity is normal, but as you get closer, things get weird. For massive particles, stable circular orbits are only possible down to a certain distance, 6 times the Schwarzschild radius, which is related to the black hole's mass.
6, I mean, I think I saw that.
Right, 6 meters. Inside that, down to 3 meters, circular orbits are unstable. Any nudge sends you either spiraling in or flying away. And 3 meters is the closest possible circular orbit, even for light. That 6-meter boundary is called the ISCO.
The innermost stable circular orbit. Okay. What if you just fall straight in?
For the person falling in, let's say, an unlucky astronaut, they cross the event horizon in a finite amount of their own time. The journey to the singularity is actually quite quick, depending on the black hole's mass.
But for us watching from far away,
it looks completely different. We'd see the astronauts slow down as they approach the horizon, taking longer and longer to cross each bit of distance. Their image would get redder and dimmer due to gravitational redshift and time dilation.
So they look like they freeze at the horizon.
Effectively, yes. They'd seem to take an infinite amount of our time to cross, fading out completely before they ever appear to reach it. It's a profound difference between the local experience and the distant observation.
Truly mind-bending. Okay, but most black holes probably aren't static like Schwarzschild. They spin, Kerr black holes.
Exactly. Roy Kerr found the solution for rotating black holes. Rotation adds a whole new layer of complexity and introduces a new region. the ergosphere.
The ergosphere, that's outside the event horizon.
Yes, it is. It's a region where spacetime itself is dragged around by the black hole's spin. It's called the lens-thirring effect, or frame dragging.
Dragged around how much?
So much that nothing inside the ergosphere can stay still relative to a distant observer. You're forced to rotate with the black hole, even light.
Wow. So even light gets swept along.
Yeah.
But you can still escape the ergosphere if you're outside the event horizon.
You can, yes, but you'd need to exert energy, fire your rockets against the current, so to speak. It's possible to extract energy from a rotating black hole via processes within the ergosphere, like the Penrose process.
And this rotation, this dragging of spacetime, this must affect how we see things around black holes, like those accretion disks, like the Event Horizon Telescope images.
Absolutely. We can't image the black hole itself, the shadow, but we see the superheated gas swirling around it in the accretion disk, and the intense gravity bends the light from that disk dramatically.
Bends it how?
So severely that you can actually see multiple images of the same spot in the disk. Light rays can take different paths, some even looping around the black hole before reaching us. You might see the back of the disk bent up over the top.
And that famous image of M87, the black hole shadow with the bright ring, where one side is much brighter.
That brightness difference is a direct consequence of the rotation and relativistic effects. It's called relativistic Doppler beaming.
Doppler beaming, like the Doppler effect for sound.
Similar principle, but with light and at relativistic speeds. Gas in the disk rotating towards us appears much brighter because its light is blue shifted and intensified. Gas rotating away from us appears dimmer, red shifted. That asymmetry is powerful evidence for the spin and the extreme environment.
Incredible. Now, you mentioned something really surprising earlier about pole thermodynamics, like actual laws of thermodynamics applying to black holes.
It's one of the most profound theoretical discoveries, yes. It started with analogies. Physicists noticed mathematical similarities between black hole properties and thermodynamic laws.
What kind of similarity?
Well, there's a Zeroth law. The surface gravity, which is like the black hole's gravitational pull at the event horizon, is constant all over the horizon, analogous to temperature being uniform in thermal equilibrium.
Okay.
Then a first law. Changes in the black hole's mass are related to changes in its horizon area and its angular momentum, similar to how changes in energy are related to heat and work in thermodynamics.
And the second law, which is about entropy always increasing.
That's the most famous one. The area of a black hole's event horizon never decreases in classical processes. If two black holes merge, the final area is greater than or equal to the sum of the original areas. This looked just like the second law of thermodynamics, where total entropy never decreases.
But these are just analogies initially, right? Where did actual temperature and entropy come from?
That leap came with Stephen Hawking. By applying quantum field theory in the curved spacetime around a black hole, he showed that black holes aren't perfectly black. They should radiate particles thermally.
Hawking radiation.
Exactly. A black hole has a genuine temperature, inversely proportional to its mass. And if it has a temperature and follows these thermodynamic-like laws, it must have entropy.
And the entropy is related to the area.
Proportional to the area of its event horizon. The Bekenstein-Hawking entropy. It's a staggering result. Linking gravity, area, quantum mechanics, Planck's constant is in the formula, and thermodynamics, entropy, temperature. It suggests information might not be entirely lost in a black hole.
Wow. So they're not just cosmic vacuum cleaners, they're thermodynamic objects in a quantum sense. That's huge.
It's a major driving force behind the search for quantum gravity. Theories like string theory and loop quantum gravity are trying to provide a microscopic explanation for this entropy, counting the quantum states that give rise to it.
Okay, bringing it slightly back down to Earth, or at least back to formation, there was that simple model, Oppenheimer-Snyder.
Ah, yes, a classic calculation. It models the collapse of a perfectly uniform, pressureless sphere of dust. It's simplified, obviously. No rotation, no pressure gradients.
But it showed collapse was inevitable.
Under those conditions, yes. It fulfills the requirements of Penrose's singularity theorem, showing that collapse leads inexorably to a singularity. It also helped explore the idea of whether the singularity forms inside an event horizon hidden, or if it could form without one, a naked singularity, visible to the outside universe.
Does the model suggest naked singularities are likely?
It depends on the initial conditions of the collapse, but the general thinking, the cosmic censorship hypothesis, suggests nature might forbid naked singularities, always clothing them in an event horizon, but it's still an open question.
And those collapse times you mentioned, they were incredibly fast.
Startlingly fast. Earth, if it collapsed, would take maybe 15 minutes. The sun, half an hour. A white dwarf, just seconds. A neutron star, a fraction of a millisecond. Gravity acts fast when it wins decisively.
Okay. From the stellar scale in black holes, let's zoom all the way out. The universe itself, its origin, its evolution, its fate. And we can't talk about that without dark matter and dark energy, the invisible heavyweights.
The dominant ingredients, it seems, yet we can't directly see them.
What?
Dark matter. Its gravity basically holds galaxies and clusters of galaxies together. Without it, galaxies would fly apart, structures wouldn't have formed the way they did.
We see its effects gravitationally, but we still don't know what it is.
Not for sure. That's a huge puzzle. Our simulations using the cold dark matter model work incredibly well on large scales, reproducing the cosmic web of clusters and filaments.
But not perfectly on smaller scales, like within galaxies.
There are some discrepancies, yeah. How dark matter is distributed in the cores of galaxies, the number of small satellite galaxies, things aren't a perfect match yet. Which is why there's this massive, multi-pronged effort to detect dark matter particles directly, indirectly, or create them in colliders, still searching.
And then dark energy, even more mysterious.
Arguably, yes. It's
Mhm.
this thing that seems to permeate all of space and has a kind of repulsive gravitational effect. It's causing the expansion of the universe to speed up.
Which was a huge shock when it was discovered, right? Everyone expected gravity to be slowing things down.
Completely. It was discovered in the late 90s by teams looking at distant supernovae. They were trying to measure the deceleration of the universe and instead found acceleration, a Nobel Prize-winning discovery that turned cosmology on its head.
So something is pushing space-time apart, faster and faster. But before we even knew about dark energy, the basic Big Bang model had its own issues, the problems.
It did, yeah. Things that the standard hot Big Bang model couldn't easily explain. One was the horizon problem.
That's about how uniform the universe looks, like the cosmic microwave background radiation.
Exactly. Opposite sides of the observable universe are now billions of light years apart. They couldn't have exchanged light or heat signals since the Big Bang to even out their temperatures. So why do they look almost exactly the same temperature down to tiny fluctuations?
Okay. What else?
The flatness problem. Observations suggest the universe is very, very close to being geometrically flat on large scales. This corresponds to a very specific critical density.
Why is that a problem?
Because if the early universe wasn't exactly flat, any tiny deviation from flatness would have been massively amplified as the universe expanded. For it to be so close to flat now, it must have been flat to an unbelievable precision right near the beginning. It seemed like an absurd fine-tuning, like balancing a pencil on its point for 14 billion years.
Right. Seems unlikely to happen by chance. And the third one, magnetic monopoles.
Yeah, theoretical particles like magnets with only a north or only a south pole. Grand unified theories predicted they should have been created in huge numbers in the very hot early universe. But we've never seen one? Where did they all go?
Okay, 3 big puzzles. How did we solve them? Or how do we think we solve them?
The leading idea is cosmic inflation, proposed by Alan Guth and others. It suggests that in the tiniest fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid exponential expansion.
Like faster than light expansion.
The space itself expanded faster than light could travel through it. Imagine the surface of a balloon inflating extremely quickly.
How does that help with the problems?
Well, that super rapid expansion would take a tiny, causally connected patch of the early universe where everything could have evened out its temperature and stretch it to become enormous, much larger than our entire observable universe today. That solves the horizon problem. It would also stretch space-time itself so much that any initial curvature would be flattened out, just like the surface of that balloon looks flatter as it gets bigger. That solves the flatness problem.
Makes sense. And the monopoles.
Inflation would dilute them. If they were created before or during inflation, the exponential expansion would spread them so far apart that the chance of finding one in our observable patch of the universe becomes vanishingly small.
It does one more thing, right? Seed structure.
Crucially, yes. Tiny quantum fluctuations, ripples in spacetime that exist on subatomic scales, would have been stretched by inflation to enormous astrophysical scales. These slightly denser and slightly less dense regions became the seeds around which gravity could later pull matter together to form the first stars, galaxies, and clusters. Inflation provides the blueprint for the large-scale structure we see.
Wow. Okay, so inflation is a powerful idea. Now, when we look out, we talk about the observable universe. What exactly does that mean? You mentioned the age versus the size earlier.
Right. The universe is about 13.8 billion years old. But the edge of what we can see, the observable universe, is about 46.5 billion light years away in any direction.
Because of that expansion during the light's travel time.
Precisely. The light from those distant objects has traveled for 13.8 billion years to reach us, but the space it was traveling through has been stretching the whole time,
Right.
so the source is now much farther away. That 46.5 billion light-year radius defines our current cosmic horizon, the curtain, beyond which we cannot see, simply because the light hasn't had time to get here yet.
And within that observable bubble, is everything just uniformly spread out?
Not quite. There's this idea of the end of greatness. On the very largest scales, bigger than maybe 300 million light years, the universe does look pretty much the same everywhere, homogeneous and isotropic.
But below that scale.
Below that, gravity has had time to clump matter together. You see the cosmic web, vast filaments of galaxies and clusters surrounding enormous, mostly empty voids. Structure dominates over smoothness on smaller scales, still vast but structured.
And the sheer amount of stuff in that observable volume is staggering.
It's almost incomprehensible. Estimates suggest maybe 2 trillion galaxies, each with billions or even hundreds of billions of stars. The total number of stars is estimated around 10 to the power 24.
Which is a lot.
It's famously more stars than all the grains of sand on all the beaches on Earth, and likely a comparable number of planets. It's a staggering amount of cosmic real estate.
Mind-boggling numbers. Okay, so we have this vast, expanding, accelerating universe. What's the ultimate fate? Where is this all heading?
Well, that acceleration driven by dark energy seems to be the key. The current rate is something like 44 million miles per hour faster for every 3.26 million light years of distance.
So things farther away are receding even faster. What does that mean long term?
It means galaxies will become increasingly isolated, mergers will stop. Eventually, the expansion might even overcome the gravity holding individual galaxies together. Star formation will slow down, eventually cease as the available gas gets used up or spread too thin. Over truly immense timescales, trillions upon trillions of years, stars will burn out, black holes will evaporate via Hawking radiation, protons might decay. Everything just cools down and spreads out.
Leading to the heat death.
That's the most widely accepted scenario based on current physics, yeah. Heat death, or the big freeze. It's based on the second law of thermodynamics. The universe reaches a state of maximum entropy, maximum disorder. Everything cools to a near uniform temperature close to absolute zero.
So no more structure, no more complexity, no more work can be done. Like that cup of tea cooling down.
Exactly like that, but on a cosmic scale. A final state of cold, dark, empty equilibrium. Pretty bleak, perhaps.
Unless our universe isn't the only one. The multiverse idea offers a different perspective.
It certainly does. It's highly speculative, of course, stemming from ideas in inflation and string theory. The concept is often pictured as a cosmic ocean, where different bubble universes constantly inflate and pop into existence.
Each with potentially different laws of physics.
Some might be like ours, others could be wildly different fundamental constants, maybe even different numbers of dimensions. Our universe would just be one bubble among potentially infinitely many.
But if we can't access or observe these other universes, is it still science? Or does it become philosophy?
That's the heart of the debate. If a theory makes no testable predictions, can it be considered scientific? It definitely pushes the boundaries, representing the edge of our understanding where science mixes with philosophy. It raises profound questions about reality itself.
And all these extreme ideas, the Big Bang, singularity, the singularity inside black holes, this is where our two great theories, general relativity and quantum mechanics, collide, isn't it?
Precisely. They are the two pillars of modern physics, incredibly successful in their own domains, GR for gravity and large scales, QM for the small scales. But they give incompatible descriptions at these extreme points. That clash is the fundamental driver for seeking a unified theory of quantum gravity, the holy grail of physics.
What an incredible journey we've covered, from how a star's mass seals its fate, leading to a quiet fade-out as a white dwarf or spectacular supernova, maybe leaving behind a neutron star or even a black hole.
Yeah, and diving into those black holes, the event horizon, the ergosphere for spinning ones, that bizarre connection to thermodynamics through Hawking radiation and entropy.
And then zooming out to the whole cosmos, shaped by invisible dark matter, pushed apart by mysterious dark energy, potentially born from a quantum fluctuation inflated to cosmic size.
And heading towards a potentially cold, empty future, unless maybe, just maybe, we're part of something even grander, a multiverse. It really puts things in perspective.
Absolutely. You've definitely got a much deeper understanding now of these huge cosmic concepts, hopefully with a few aha moments mixed in.
We covered a lot of ground.
We did. So, as a final thought to leave you with, we've talked about dark energy ruling the largest scales and quantum fluctuation seeding the smallest structures that grew into galaxies. Given how these almost undetectable, counterintuitive things fundamentally shape reality as we know it, what else might be out there, influencing the cosmos in ways completely beyond our current senses or instruments? What's the true nature of the reality underpinning everything we observe? Something to ponder.